Yeah, so normally when you took this class in differential equations, they were taught you tricks on how to do integration of differential equations. Uh, Example would be uh, a pendulum going back and forth, equation of a ball being dropped in the sky. Uh, let's set a horizontal, certain horizontal vertical speed, that would be a differential equation and so on. So a general ODE, this is known as a ODE, will look like this. F x y dy dx t square y dx square so on dn yn dxn equal to 0. So this is just saying that the uh, function doesn't have to be just a function of x and y. It could also be a function of the derivatives. So that equation equal to 0, where x is the independent variable, a common one is time, and y is the dependent variable. Okay, so y depends on x. Here, what we're trying to do is we're trying to figure out what's the relation between y and x, like we've always been interested in. Some things are best described by differential equations, like, for example, as I said, the pendulum and so on. You cannot write a formula, but for a pendulum, you can write a formula for the angle of the pendulum as a function of time, but many problems you cannot write it analytically, and so you need to resort to um, some kind of a numerical method. Now, when I say a function f is like this, I also need to give some initial conditions. So to solve an ODE of order n, uh, n being the highest derivative in this equation, dn by dxn, I need to give you at least n initial conditions. We need n conditions. Okay, the simplest way to write these conditions are what they call an initial value problem. Uh, Here we're given the values at x equals 0. Are given. Okay, so those are given, and you need n conditions, so as you cannot solve n conditions. Now it turns out that there are two types of ODEs. This one would be what they call a initial value problem, because all the conditions are given at x equals 0. All conditions at x equals 0. There's another type of problem called a boundary value problem, where some of these conditions may not be given at time t equals or x equals 0. For example, the simplest way is if you had given something at x equals 5, say. So here note that only one condition is given at x equals 5. Now, the moment you have one condition given at a different value other than 0, then this problem is known as a boundary value problem. Value. So at least one condition at least one condition, not at x equals 0. Okay, so this thing is often abbreviated as IVP, and this thing is often abbreviated as BVP. And I don't know if you guessed this, but one of them is easier to solve than the other one. The IVP is easier to solve than BVP. And the reason is because if you want to solve an BVP, so take that first equation, y5 dy, you do not know what happens at y equals 0. So many times the BVP will involve solving an IVP multiple times. So if you start with, you'll assume a guess for y0 for the BVP, you'll integrate ahead in time, see if you get the desired y5 value. If not, then you'll try again, and you keep doing that till you get the right value. And there are smart ways to do that using, you could actually use root finding, something we've learned in the past to do that. So those are harder to solve. Now there's one more thing before we go to and solve a problem. Well, we go to the methods. When you're given an nth order equation like the one I wrote down here, you want to always break it down into n first order equations. So this equation here, this one, is the nth order equation. You always break it down to first order equation. So once you break it down to first order equation, we have tools to solve those. So to solve ODE of order n, break it down to n first order equations. So how do we do that? So we wrote down this equation, xy dy dx d square y dx square, so on till dn y dxn equals 0. So the way we do this is we'll define new variables. Let's call them y with a uppercase y. So let's call that y0 equals y, y1 equals dy dx, okay, y2 equals d square y dx square, so on till we reach yn equals dny dxn. Okay, that's the first step. The second step is to write n first order equations. So n first order equations. How will we do that? We'll use these uppercase y's to do that. Okay, so it should be fairly easy to see that if you do dy1, sorry, my bad, dy0 dx. Okay, so what's dy0 dx? It's basically dy dx, right? Just the derivative of this. But what is dy dx? It's right here. It's y1. Then we do dy1 dx. So we need to take the derivative of y1 with respect to x. So that will be d square y dx square. How do I get this? I took this and I took the derivative of this. So that is nothing but y2. So you can ignore this part for a moment. This is just for us to make the connection work. But dy0 is y1, dy1 is y2, and so on. Till we hit dy n minus 1 n minus 1 dx equals yn. Okay, so those are the n minus 1 equations, and then we need one more equation. That would be dy n dxn dy n dx equals, so we'll use this equation. This is uppercase F. Hopefully we can isolate this particular variable. So if we can isolate it, like pull it out, then everything on the other side will move, will become our equations of interest. So it will be, so when I say isolate, I literally mean, if you could write this as dn y dxn equals, let's say the lowercase f x y dy dx and so on, then you'll take this equation and that will become your last equation. It will be f of x, now y is y0, y1, y2, so on till y n minus 1. Okay, so now we have n equations, and we can solve for those. Well, actually n plus 1 equations. Okay, so let's see how to do this. I think sometimes it's not very intuitive, and it's best illustrated with an example. So let's do a case where we have a third order equation, and then we'll see how to break it down to first order equations. So here's the problem. Sample. So given this equation, d cube y dx cube plus 2 d square y dx square plus y plus x square equals 0, rewrite as first order equations. Okay, so you notice that in this equation we have the highest power is d cube dx, so cube. We do not have a dy dx, but that does not mean dy dx will not be in the equation. There will be a dy. In fact, you'll go right from dy dx d square y d cube y. So let's do the same trick we did earlier, but before that, let's just do this step of isolation of the variable. So here we isolate d cube y dx squared. It will help us later on. So d cube y dx cube is minus 2 d square y dx square minus y minus x square. Okay, that's the first step. Now let's introduce variables. Y0 is y, y1 is dy dx, y2 is d square y dx square, y3 is d cube y dx cube. Okay, these things will help us write down the 4 equations. Okay, so what are those equations? Well, first we'll find what is dy0 dx. So you see that to compute dy0 dx, you just need to do dy dx. But dy dx is nothing but y1. So you can just skip this. It's just sometimes confusing to put that in. So that is, well, let me just keep this here so that when you refer to this, you will see the how it came. But you can just ignore that if you think that's confusing. Then you can do d square y, sorry, my bad, dy1 dx will be the derivative of, see this here, it's dy dx. So the derivative of y1 with respect to x is d square y dx square, but d square y dx square is y2. Then we have dy2 dx is the the derivative of the second derivative, so third derivative. That would be y3 right here. And then dy3 dx I don't think I need y3. Yeah, so my bad. I don't think I need this. Okay, why don't I need it? Well, if you see this, I already reached y3, but y3 is, I don't need this. Why I don't need this? Because if you look at this expression now, I need to substitute this value, but it's right here. So that value is actually in terms of the lower derivative. So I really don't need an extra variable. So my bad, I shouldn't go to y3. So this should be here minus 2 d square y dx square minus y minus x square. But I don't keep it in terms of y, the lowercase y. I need to keep it in terms of uppercase y. So here it would be minus 2 d square y dx square is this, just y2 minus y minus x square. So this is my last equation. This is just to help you to write the equation, but the equations are 1, 2, and 3. So 1, 2, 3 are the necessary equations. Okay, again, my bad. This y, I don't going to keep any lowercase y, so that will be actually uppercase y, 0, right? Again, this is not needed. This came from, so if this is, let's call this 1, or other, I have used 1, okay. Let's call that A. This is from